and tell a little bit about the different approaches in the life cycle, and then use the pump life cycle story as an example, and then go to the main part, how we modeled these requirements with IDO. And I will finish with a small conclusion. Yes, the flexible production value networking project will end this summer, and now we have first results, and results about work package 3 I will present, and Onno will tell something about CFOS, how it could set up a semantic interface to IDO, Torbjörn with ISO with STEP, with the 2 application protocols to IDO, and my task is to tell how DEXPI can be modeled on a semantic level to IDO, especially with the view on the life cycle. For the life cycle, there are additional or some approaches, and the typical here is simplified model of the integrated asset lifecycle information management model with process development at the beginning, engineering, construction, and the long phase with production and maintenance. And with the thinking in the disciplines, we have to integrate the disciplines, and what's important to set up a complete asset lifecycle information management model over the whole life cycle from beginning at the process development, perhaps at the end to decommissioning. And there were some, in the last years, some concepts how to do it. At the beginning, we define the functional requirements and end with information structure as a process structure. And based on that process structure, a plant design, a functional design will take place. And after the functional design, there is the asset specification in detail engineering, all based on a plant structure. And then the construction will take place, and then we have the asset in operation, and we have an asset structure. That is a fundamental view on the life cycle, and let's say we have 3 information structures important with the process structure, the plant structure, and the asset structure. And based on results from the ISO 15926 researches, there is a big model for that, a life cycle stage model. And here we can see to the left, there are all the classes and activities around the process. In the middle, around the plant. We'll use for that colors, orange for the process and blue for the functional view on the plant, and green for the physical view, for the specification view on the plant objects. And then to the right, we have first of all the dark blue things for the vendor market with product models. And then, of course, an owner operator or an EPC buys these products, and they were invented as assets in the view of owner operator. And of course, for a maintenance system, we have to have a relation between the assets and the plant items. And if we go to CIFOS, perhaps Onno has it also in his slides. To the left in the data model, we see the world of the process. In the moment, in the middle, the tag world, and on the right, the world of the assets. And in CIFOS, they were called equipments and tags. That were the main classes which were handled in CIFOS. And additional things that there were additional asset types. But in general, we see it's the same look on the life cycle, on the information structures. And if we go perhaps to the BIM world of construction, they have this model with the 4 quadrants. And on the upper level, we have the functional entities as planned and realized entities. And the lower level, with technical entities as planned entities and as realized entities. And in this picture, we can put in our information structures as well. To the left, on the bottom, we have the process with activities and streams. And this one is not one-to-one. We should say, okay, the design, the functional design of the plant, that is more the functional world, but the green world with the technical specification of the different assets, that is on the technical entity level. And to the right, we have the constructed plant with its assets.
Japanese.
And
I really want to learn Japanese.
There is some noise in. Okay, I hope not for everyone. And here to the right, there is afterwards the producing plant. In my next view, we will concentrate us on the three information structures for the process, for the plant, and for the assets. And that one for the specified and the actual part of it. And as I could show you, we have a nearly good alignment on the view of the life cycle in the process industry from ISO 59226, from CFOS, from DEXPI, and from BIM. They are quite aligned. And we use the pump life cycle story as an example for the modeling to IDO. Represented here perhaps as a block flow diagram with a very small snippet, pumping in the middle, storing before, and a chemical reacting afterwards, connected by process streams. And we have here an inlet port and an outlet port on this picture. The same content in another diagram as a process flow diagram is here presented on the lower part. And we see we have the process breakdown structure here to model. We have the process object and the components, and we have the model properties. Today, we will concentrate us on more on the life cycle things. What we have to model here is always on both. Here we see instances, but as first, we have to model the class world as well. And the next step is for the process plant. Here we concentrate us on a pump system. The pump system has a pump, has a motor, has an instrumentation function. The pump itself has some nozzles, and to the left and right we have piping network systems. And we have some first properties, but that we will do in a later session, end of May, to explain it, how we can model these properties. And here, for the pump life cycle story on the plant level, we have, okay, the plant breakdown structure to model, then the plant objects and the component and the properties. And of course, we have to model the important bridges between the process world and the plant world. And beyond DEXPI, we have a model for process and plant. We have the asset world, but in our story, we use the asset part as well, the asset information structure. And we see, okay, we have the objects as products, and we have the assets objects, and the assets must be related for plant maintenance with the plant objects. And the modeling results, I will show the modeling results. We have some here. First of all, the first decision was to look all the classes we have, we need for the process world. Here, that are the terms for in ISO 59226 Part 4, the DEXPI class names, and here we have PROC means we have for the process in an ontology, and that were the classes which we put in this ontology, and all classes are modeled as lists in IDO as list activities. Let's say the whole process world is modeled as an activity network, an important decision. And here we have a very a populated picture for a pump example for the unit operation pumping OU2, and it's very populated, and therefore I will reduce this. To the left, all the yellow parts were in that were instances, and these instances were modeled with this part of a whole process step. This pumping unit operation itself, it has parts like the two material ports, and it has to have some relations to the streams. And for the internal relations of a process, there were not enough object properties in IDO, and therefore we propose to extend IDO with list extension and add some object properties to to fulfill the requirements that we can have the connectivity modeled for the process as well. And here we see something like list extended feeds or delivers to. That were some extensions. And of course, the instance model is related to the class model. Here in blue, we see the pumping, the unit operation, and the material ports and the streams. And the next step is that we have the from the classes, not from the instances, from the classes, the relations to the list class world. Main thing is that we have here, as I said, everything is modeled as list activity, and to support the additional range and domain requirements of the new object properties, we have some new classes for process activities and port activities. And we have matches with cost exact matches to the part 4 definitions for pumping, unit operations, port in, transport, and process streams. And now that's the full picture how we have modeled the pumping activity as a part of the whole process. Let's go to the next step, to the specified plant. Here we see that we have systems and inanimate physical objects. The systems were the blue objects in the picture, and the green objects were modeled as inanimated physical objects, like our typical example, the centrifugal pump. And we see here an additional ontology for these classes, and we said, okay, these classes, we say that are the specified classes. We distinguish between the centrifugal pump, between a specified centrifugal pump, and later we will see that we have it for an actual centrifugal pump as well. And here are for the physical equipment, we see it for in purple, we have classes here for the actual centrifugal pump as well, also classified in IDO as inanimated physical objects. And that means that the specified and the actual centrifugal pump are classified in the same way on class level. We will see now that we have for the classes to relate them, or for the big information structures, we have object properties like list has participant and list participates in, to relate the process instances to the plant instances, and on the other side we have the list implemented by and list implements to have the relations between plant objects and assets. And that is done on instance level, and that means from list implemented by, and it's reversed to the IDO classification, list specified and list actual. This one is inferred now on instance level. In that way, we use and support list specified and list actual on that way on instance level as well. And here we see picture as a graph picture, and we see to the left the process, to the right the specified plant, and the object properties has participants and participates in, and the same for the next step between the specified plant and the actual plant. We use the object properties implemented by and implements to the left and right. And now a quick conclusion. Yes, the process structure is modeled as a complete activity network. Some new object properties were required. Classes for specified plant are modeled with list system and list animated physical objects. And the classes of actual plant as well with list animated physical object. There's no distinction on class level, but with inferred relationships, we have on instance level the distinction between specified and actual. And that is a quick overview how the life cycle requirements were specified for the DEXPI part with IDO modeling parts. That was my part, and now Onno, your part.
Okay, thank you, Heiner. And we saved the questions until the end. So, as you said, Onno takes over.
Yeah, hello. So I'm going to spend my 15 minutes on CFOS semantics. But I'm working in a number of projects. So ISO 1596, CFOS, Arrowhead. And I'm also participating on DEXPI. So we intend to harmonize those 4 projects and not make competing standards, so to solve it all in the same way. So that is why I can now tell you how that works for CFOS semantics. First of all, I want to explain a little bit why we are doing this. So CFOS semantics is a team within CFOS. And CFOS is 80 companies working together for data handover from engineering side to the owner-operator side. But we also want to work into semantics. So we set up the project, but we still have to do our first feature request, by the way. And we are still thinking, okay, how can we transform the entire CFOS RDL, the library, and the data model to semantics, and that is proven to be difficult. But why would you do semantics at all? So that is what my first slide is about. So the reason that we started this is what it delivers for you, for the participants of CFOS. And by the way, CFOS is a membership project. However, all the products are in the public domain, so you can just go ahead to the CFOS website and download all of our products. And if you ask, you can get more from us, the participants in CFOS. So if you go to semantics, first of all, you never do everything to semantics. It is always working together of relational databases, so SQL databases, and a semantic database. And so you can have many sources in the SQL databases, and one central semantic database that will have all that data as well. Is a copy of that other data, other source data, and but in the semantic database, it is all data integrated, and you can reach everything, and it is queryable, and it is fast, and you have everything on one screen. So that is what you're talking about for a semantic database. So if you have one, that means faster projects because of the availability of the data, obviously. There's a quicker data handover and onboarding of contractors and suppliers. Change is handled without redesigning schemas or templates. We have trustworthy automation, so the system is keeping itself up to date from all the available data sources. On an engineering project, it can be up to 40 data sources. The P&D software, the document management software, the equipment database, instrument database, electrical database, all those data sources, spreadsheets, line list. So the semantic database will keep its consistent meaning across tools available validation. You can use AI, digital handover. AI and semantics is hand in glove. It works perfectly together. There's less dependence on PDFs, spreadsheets, human interpretation. Therefore, there's a lower lifecycle cost because of the complete data integration. There's fewer late fixes, less rework, less manual reconciliation. Information stays usable as requirements and regulations change. So this is for engineering companies really, really important because, you do a project in parallel. You start everything together, and then every discipline is changing the data all the time, and the other disciplines have to keep up with that changing data. So really important that there is a flow of data to this semantic database. So there is a protection of today's investment due to the versatility of semantic ontology. So if you have these CFOs, that remains valid as the standard evolves, because the semantic database, the ontology will grow with CFOs. There's no lock-in to specific tools, databases, or vendor models. So the bottom line is semantics lets CFOs scale with your business rather than constrain it. But today we are talking about an aspect of semantics, and that is the life cycle. The life cycle quadrant was already shown to you by Heiner. Here it is again. There's 4 quadrants, and so as mentioned, it comes from BIM originally, but we already have it in 1596 for a while. So the left-hand side is the tech, and the right-hand side is equipment. But in the other standards, for example, IDO, they would call it specified and actual, but that is regarded to be a synonym in process plans, process and power plans. And the top is functional and the bottom is physical. So if you start in quadrant 1, we started process design, narratives, the activities that Heiner showed to you. Then P&D schemas, instrument index, one-line diagram stuff, and equipment summary. And then you move to requisitions and 3D model. That is the physical object, because now you're designing, you're engineering how it should work physically, and the layout and the available space. Then when the equipment is being bought and delivered and installed, you get vendor data, and then it moves into commissioning, operations and maintenance, and then you get an as performing functional block. So that is also how we are designing up our functional, physical and tech and equipment side. In CFOs, we are mapping the data from the JIP33 project, and that, to me, gives the best example of why there is a tech and equipment side to all of this. In JIP33, it is really clear. So here's a little piece of a centrifugal pump datasheet, just like 20 or so of the 1,200 distinct data elements that the pump datasheet has. But in JIP33, there's only 350, and I say only, but that is of course a huge amount. The red ones are to be filled in by the purchaser, and the blue ones are to be filled by the supplier. The gray ones do not need to be filled in. And you can see that we have specific properties for the purchaser and other specific properties for the supplier. That is why there is a tech site and an equipment site. They have different properties. There's different things to say about them. And that is also important for this aspect that we are talking about, this life cycle aspect. Because when we get the vendor data, so that is the blue stuff, we want to compare it to the requirements, that is the red stuff. And we want to have those data sets available to be compared. And it is not easily compared. You cannot compare it value to value. Now you have to make rules and requirements. They need to be interpreted by engineers. But we are intending to have programs, of course, look at that in the future. So I said that. The centrifugal pump would have 250 properties in CFOS. So in this case, it would be 250 for the tech side and 150 for the equipment side, and 100 of those are the same for both sides. So how many are we talking about in CFOS? And then I'm saying, okay, we are talking about 12,000 distinct properties. So there's no way that we can do this manually. That must be handled by automatic tools. And that is why we are doing so much trouble of doing this data modeling and making it all work. And by the way, only a semantic database can have the entire overview of all of those. So how does this work with IDO? So what is IDO? IDO is an upper ontology. Upper ontologies, they have just a few classes, 40 or so, and a few relationships. And that is because when you have a domain ontology, so CFOS is a domain ontology. And I said we are talking about 2,000 equipment classes. We are talking about 5,000 or so lookup values. We are talking about 12,000 properties. That is a domain ontology. So compared to IDO, that is a big difference. So what does IDO bring us? Well, you can say that equipment, that is the tech equipment and the tech and the instances and the equipment instances, so the valves and the pumps and the pipes and the vessels, that they are specified or actual. So that is one as well. Then there's a taxonomy that has classes. So the class is a subclass of something in IDO. And that gives them specific domain and ranges. So extra relationships that you can give it, meta relationships. So that is what an upper ontology brings you. And you can see it best here with the property. So at the bottom you see here assigned property and dependent property. So assigned is but you can give it without the class changing every time. So you can give it a tag number, for example, and you can change the tag number. You can give it a required assign date, all kinds of assigned properties. And a dependent property is, for example, the material of construction of something. If you change that, then you have a different thing, a different type. So you have to split up your properties to assigned and dependent, and if it is a designation or just a string, if it is a quality or a physical quantity, you have to split it up like that. And you and I know that our properties are not split up like that. They are just a list in CFOS, a big list, and also in JIP33, that's just a big list. So we are connecting up aspects to those properties, meaning to those properties. And these aspects and meaning will give you the opportunity to split it up like this and make it work properly, so that programs so like AI can find the meaning of the properties, not just the English word or sometimes even a single English word that they have to decide what it is. Now these properties have definitions and they have aspects, they have meaning, they belong to a place in the taxonomy. So that is a big difference. It's much better to work with that. Now, and finally, I can show you how we are doing this thing with specified and actual. If you would give all the pipes and valves and pumps and vessels a relationship to what life cycle aspect they are, life cycle states they are, that is a nightmare. That is a million relationships. So we've already done this in our company. We are using named graphs for that. So the data set of required, the specified stuff, and the data set of the delivered or the actual stuff are two different data sets here, and now they can be compared to the requirement to the delivered. And if they, if the owner operator replaces equipment, that engineering team can still look at the requirements for that equipment and then decide what other equipment to take instead. So they don't have only the equipment, the actual equipment as data. So yeah, we are moving along, and please join the CFOS activity. Thank you.
You Onno, it's almost exactly on time. So I think we just move ahead and leave the floor to you, Torbjörn.
Yes, I'm Torbjörn Holm, and I will talk about the Arrowhead FPVN use case 2.9 process plant, it's called. And the use case owner is Stora Enso, a paper producer in Sweden. And this is an implementation, since not everything that Heiner and Onno was talking about was available when we started this implementation like one and a half year ago. We have a little bit of mixture of historical decisions in the implementation. Still, it works, and that's rather interesting. We can benefit a lot from these things, even though if it's not really perfect. We are using this architecture. We have IDO on the top, industrial data ontology, and then we have the DEXPI ontology. You see it here. And we have a step core ontology. Step core is the overlap between AP239 and AP242. And this is carrying a lot of the information in this use case. And then we have something very interesting, Arrowhead framework ontology, which is the Arrowhead framework on ontology dealing with the data that is processed dynamically in the Arrowhead framework. And I will talk a little bit more about that. We have, of course, data. DEXPI data, we got through Semantum, who transferred PNIDs to RDF. We have step data that we got from different sources, mainly SAP. And then we have the cyber-physical system as an ontology with all sensor data. So this is then they are aligned, not merged, this ontology. So this is the aspect of a tag from a system point of view. This is the aspect of a tag from a solution point of view, as well as part and individual parts here. And here is a lot of sensor and sensor data and connectivity to things that they are measuring. We have also integrated a 3D viewer from Cadmatic, and we are using an SAP mockup for SAP HANA mockup for the work order processing, because this is about also finding out problems, creating work orders, resolve the work order, change it, and update knowledge graphs. I think that's it. You will have the slides later. What we are also doing is that we are using the reference ontology, and in our case right now we have a mixture between CFOS and ISO 15926-4, and we are classifying the tags, the DEXPI tag and the step tag, using CFOS tag classes, and we are also using CFOS equipment class to classify both the parts and the individual parts. This is really important, that makes it possible to do this very large models or ontologies or knowledge graphs, because there's so many different classes that we deal with in a running paper machine. The principles we are using alignment. We have aligned the tags between DEXPI and STEP, and we are using, we have an extension to IDO where we have the tag identity, and we match this, we align this, so we know that this is the same. The DEXPI object instance is the same as the STEP instance. We also deal with this kind of structure that the DEXPI is an upper ontology, it has the IDO as an upper ontology, and STEP has the IDO as an upper ontology. We also have AFO, the Arrowhead Framework Ontology, and that's totally aligned with IDO, while DEXPI and STEP are partially aligned with IDO, very partially really, because we have not made many alignments, but it adds a lot of benefits anyhow. We talk about two life cycles here. We talk about what is allowed to be placed in a specific function location. This is the function location. And we could have one or many pump classes. That's the part. You're allowed to place something in this place of this class. But this is also over time, it starts to be valid to use one of these, and it stops to be allowed to use it. And that puts requirements on what you do when you do a physical realization. To replace a pump or something like that, it needs to be with another pump. The new pump needs to be allowed, according to this effectivity, to be put in this function location. And that really is very important in this case. In reality, it's a little bit more, because you don't replace them always directly by one by one. So that the work order can also be more complex, like repair these things and so on. I will not talk about that now. But the important thing is that we do everything connected to activities. We don't all the dates and things like that is carried, the effectivity or the activity start and stop, they are carried by activities. But we can say that this tag was realized by one physical pump, and after this maintenance activity, it is carried out by this one instead. So this is the effectivity thing for how the configuration looks like. We talk about end-to-end life cycle overview. Heiner talked about that they had a process also, but what we have, we start with the system design, we have step physical structure, we have part specification, and we have individual part equipment, vendor view, and assets, the owner view. So we have this all, and we keep track of changes in this structure. If it's an update or a maintenance thing, then we just replace something here or repair it. But if it's a redesign, you need to go back to the system design or even to the process design and go through this whole chain. But we keep all these things over time, so we have the total history of this plant available. One important thing is this sensor data thing, because we have the life cycle data. This is the assets, parts, effectivity things, but we also have dynamic tasks and constraints. This is our maintenance things and so on. And then we have the dynamic data, the sensor data that's going on all the time, but we are keeping them in different knowledge graphs. The static one, the semi-dynamic knowledge graph, and dynamic knowledge graph. I think this was it. No, not really. So we deal with alignments, large alignments, total alignments or partial alignments between different ontologies. We deal with the realization from part to individual asset, really important, but we also keep track of what is allowed to, what part can theoretically be resolving on function location. And that's important knowledge. And we have life cycle control via effectivity and constraints. We are now polishing this in final tests, and we are going to demonstrate it in Oslo and some other times before that. It is really, really promising. Thank you.